So today we're going to be talking about set theory. But before we actually get into the set theory, we're going to be talking about some prerequisite knowledge that I think is essential to know before we actually get into sets. And this prerequisite knowledge will be based on a number of definitions and symbols that would help us to better understand when we get deeper into the set theory. Okay, so let's get right into the definitions. So our first definition is a set. What is a set? So a set is a collection of elements, and these elements can be objects, numbers, ideas, and they all have something in common. When listing elements of a set, we usually put them within a pair of curly brackets that look like these. So for example, if I were to say, list the elements of a set with the letters A to D, we begin, open curly brackets, A, B, C, D, and then we close with our curly bracket. Our next definition is multiples. What are multiples? Multiples of a number are generated by multiplying that number by 1, 2, 3, and so on. So for example, if I were to tell you, what are the multiples of the number 6? The multiples of the number 6 would be 6, which is 6 by 1, 12, which is 6 multiplied by 2, 18, which is 6 multiplied by 3, 24, which is 6 multiplied by 4, and so on. So again, multiples, multiply that number by 1, 2, 3, 4, and so on. Our third definition that we're going to look at is factors. Factors of a number are numbers that divide that particular number exactly. So for example, if I were to use the number 6 again and say, list the elements of the set with the factors of 6. That would be all the numbers that divide 6 exactly, which would be 1, 2, 3, and 6. 6 divided by 1 would give us 6. 6 divided by 2 would give us 3. 6 divided by 3 would give us 2. And 6 divided by 6 would give us 1. So these are all the numbers that could be divided by 6 exactly. Our fourth definition is prime numbers. So prime numbers are numbers that has exactly 2 factors. So we just spoke about factors, right? So these numbers has exactly 2 factors, and those 2 factors are itself and 1. For example, a set containing prime numbers can be 2, 3, 5, 7, 11, and so on until the parameter has been met. Our fifth definition is natural numbers. Natural numbers are the counting numbers 1, 2, 3, and so on in like manner. Natural numbers are represented by the letter N, which looks like this. So let's go on to our sixth definition, whole numbers. Whole numbers are the numbers 0, 1, 2, 3, and so on in like manner. Whole numbers are represented by the letter W. Now you're probably saying, wait, hold a minute, let me rewind. Whole numbers and natural numbers, aren't they the same thing? Well, they are very, very common. Let's just look at some differences between whole numbers and natural numbers. So natural numbers, as I said before, are the basic counting numbers, which starts at 1, 2, 3, 4, 5, and so on. Whole numbers, however, they start with 0. So another difference is that natural numbers are represented by N, and whole numbers are represented by W. So again, let's not forget that natural numbers start from the number 1 and whole numbers start from the number 0. Our seventh definition is integers. So integers are the negative and positive whole numbers. So integers would be -1, -2, -3, 0, 1, 2, 3, and so on. Integers are represented by the letter Z. Our eighth definition is rational numbers. So rational numbers are all numbers which can be written as common fractions or repeating and recurring decimals or integers. Rational numbers are represented by the letter Q. Our ninth definition is irrational. So irrational numbers are numbers which cannot be expressed as common fractions or as recurring decimals. So for example, the square root of 2 is an irrational number. If you take your calculators and you punch in the square root of 2, you'll see a long series of numbers that are not recurring decimals. Another example of a popular irrational number is pi, which is 22 over 7, 3.14. Right? We round it off to 3.14, but if you really divide 22 by 7, you're going to see that long streamline of numbers that aren't recurring decimals. Irrational numbers are represented by the letter I. Our 10th definition is real numbers. So real numbers now are all rational and irrational numbers. Moving on to our 11th definition, an empty set. So an empty set is just as the word said, empty. It's a set that has no elements, no numbers, nothing at all in it. Our 12th definition is equal sets. So equal sets have exactly the same elements or members. For example, equal sets would be A, B, C, D and B, D, C, A, because they have the same number, same elements, same members in it. It's just rearranged differently. So we have A, B, C, D, and the other set has A, B, C, D just rearranged in a different way. So these are equal sets. Our next definition is equivalent sets. So equivalent sets have the same number of elements or members, right? But they are not equal sets. So for example, A, B, C, D, and E, F, G, H. So we see both sets has 4 elements, and they're both letters, but they're not exactly the same. So these are equivalent sets. Our next definition is finite sets. So finite sets has elements, all of which we could list or count. So for example, if I say, let's have a set with numbers from 1 to 10. It's quite possible to list members from 1 to 10. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. However, infinite sets have elements, the number of which there's no limit, like infinity. So if I were to say, give me the set with the list of all multiples of 3. All multiples of 3 would lead us into infinity. We're going to start off really small, 3, 6, 9, 12, 15, 18, but we're going to keep going on and on and on, and there will be no ending. So that's the difference between finite and infinite sets. The universal set contains all possible elements under consideration. The universal set is represented by the letter U. For our next few definitions, we're going to be using this example to help us better understand these terms. So we have 3 sets. Set A, and the elements are 3, 7, 9, and 14. Set B with the elements 9, 14, and 28. And set C with the elements just 7. So the first definition for these examples that we're going to look at is subset. So a subset is a set within a set. So therefore, all the elements of one set can be found in the elements of the larger set. Subset is represented by this symbol here, which kind of looks like a C, like a flat, long, elongated C. So for example, C is a subset of A, because as we can see, all the elements in C, which is just the number 7, can be found in A. So therefore, every element of C is in A. Our next definition is complement of a set. So complement of a set is represented by an apostrophe. And a complement of a set describes all the elements that are not in the set. So for example, A complement would be equal to 28, because all the elements that are not in A would only be 28. If we look at set B, we see that set B has 9, 14, which are also elements of set A. If we look at set C, 7 is an element of set A. The only other element that we cannot find in set A is 28. So therefore, A complement would be 28. Our next definition is intersection of sets. Intersection of sets are represented by this symbol, which looks like an N or an upside down U. Using the example above, A intersect B would be the elements that A and B both have in common, which is 9 and 14. Our next definition is union of sets. Union of sets is depicted by a U. And union of sets contains the combined elements of the sets without repetition of the elements common to them. So using the same example, A union B is going to be a combination of all the elements of set A and all the elements of set B without repeating the common elements. So therefore it's going to be 3, 7, 9, 14, and 28. Disjoint sets describe sets that has no common elements within them. Using the example above, set B has 9, 14, and 28, and set C has 7. They both have nothing in common, therefore they are disjoint sets. The last definition that I'll take a look at is a Venn diagram. So a Venn diagram is basically a drawing that depicts the universal set as a rectangle and the subset as circles within the rectangle. So we're going to use the same example and we're going to draw a Venn diagram to represent this data. So first we're going to start off with a rectangle, and then we're going to draw circles to represent the subsets of the universal set. So first we're going to draw circle A, then we're going to draw circle B. Now remember earlier in my definitions, we already established that set C is a subset of A. Therefore, all the elements in C can be found in A. So therefore, we would have to draw circle C within circle A. Now we're going to fill out all our circles with the elements that belong to it. We can start with C, and we'll put 7 there, and that represents that 7 is in set C, and it's also part of set A. Where the two circles intersect represents intersection of sets. So that is what A and B both have in common, as we said before. So again, A and B both have 9 and 14 in common. So we're going to put 9 and 14 in the middle. Then we're going to fill out the remaining elements of A, which is 3. So now when we look at the circle A, we can see that the elements in A are 3, 7, 9, and 14. Then we're going to fill out the elements in B, which leaves us with just 28. So now when we look at B, we see that B is made up of 9, 14, and 28. This brings us to the end of our prerequisite knowledge for set theory and all the definitions that will be very useful when we go on to doing questions concerning sets. So I really hope that you were able to understand all these definitions and that you'll be able to apply them when I do my next video, digging deeper into more questions surrounding set theory. So once again, I hope you enjoyed this tutorial. Any questions or concerns, please feel free to leave a comment in the description box below. Head over to my Instagram and Facebook pages at Marshall's Tutoring. Don't forget to like, share, and subscribe.